Hi! So before we get into naming and formula writing for different kinds of compounds, it would be good to talk a little bit about how they bond. And we'll start with something called ionic compounds, which we'll spend the first part of this unit learning about. Ionic compounds are a metal and a non-metal when they combine. And so just to refresh your memory, the metals are everything over here, and the non-metals are everything over here. And that's a pretty small subset, but there's lots of different possibilities for ionic compounds, and I'm going to show you how they bond before we get into how to name them and stuff. So, excuse me, so let's get rid of those and then talk about how they actually do bond. When they bond, they have to talk about valence electrons. Valence electrons are the outer electrons in an atom, and I showed you in a previous video how to calculate them, but the easy short lesson is that valence electrons is the tall column that the element is in. So 1 valence electron here, 2 for everything in that column, then 3 for everything in this column, 4 for everything in that column, and 5, 6, 7, and 8. So those are the number of valence electrons for each atom, and they all want to have 8. And whenever any elements will bond to make compounds, the reason that they're doing that is because 8 is the magic number that gives them a lot of stability. And so to get there, they're going to pair up in different combinations so that each atom can have 8 electrons. And there's a couple ways they can do that. They can share electrons or they can donate electrons. Excuse me. And ionic compounds will donate electrons to get 8. And it's a very simple process, so I wanted to point it out to you. Let's just pick a very simple case of, let's say, sodium, which is right here, and chlorine, which is right here. Okay, sodium has 1 valence electron, chlorine has 7 valence electrons. You can represent them by dots. So I'm just going to go up here and draw a little picture of sodium as something like this. It has 1 valence electron, so that's the 1 dot it has there. And then chlorine has 7. You can represent them with 7 dots like that. Okay. And remember, the magic number is 8. And they can solve their problem kind of mutually by, if sodium could give this electron to chlorine right there, well then chlorine would have 8, which is great, right? And since it just gained an extra electron, guess what? Its charge is -1. Now sodium, you say, oh, well, it doesn't have anything. Well, actually, if you lose the 1 electron for sodium, if we go back and look here, we lost this 1 valence electron, which is right here. Well, guess what? Now you have 10 electrons, and so you're kind of like this element right here. You're not exactly neon, you don't have the same properties as neon, but you have the same number of electrons as neon, which is 10. And so, but let's count our valence electrons. Look, neon's in that column there where it has 8. So sodium, actually, when you lose that electron, it sort of goes down to now having 8 valence electrons, right? We lost the 1 valence electron, and so we're onto a new shell, and that new shell means we have 10 electrons, and so we are at 8 valence electrons for sodium. Well, guess what? Since sodium lost its electron, it's +1. And if you took physical science, or we talked about this a little bit even in class, you can see that we've got something with a +1 right there, something with a -1 right there, and we know that positives and negatives will attract each other. And so this is how sodium chloride forms. This is how all ionic compounds form. You form an ion. Remember, an ion is a charged particle, so there's one, and there's another. And then that attraction between positive and negative is what makes ionic compounds happen. And so you've heard of table salt, but this is how table salt forms, NaCl. And we're going to learn how to name them and write their formulas first. So we're going to take a break from what is ionic, what is covalent. I'm going to use a lot of words for what these things are, but really the next week or two of your life is when you look at a compound, how do you name it? And if I give you a name, how would you write its formula? That is the goal of the next few weeks of our lives. But I did want to just point out, this is how ionic compounds are formed. It's all about valence electrons. One other thing that is really important for this is that since we know that the valence electrons and what will happen for each of them, we also want to have, we also know the charges that each of the atoms will form, and that's super important. Actually, I'm going to erase some of these things so that not to be confusing. So the charges are very predictable for most of the elements in the periodic table. The elements in the middle, we don't know their charges. We'll get to that at the end. So everything, since this has one valence electron here in the first column, everything in there will form, it's going to lose that valence electron. Remember, the goal is to get to 8, so it's going to lose its valence electron. So everything in the first column forms a +1 charge. And likewise, everything in the second column would lose 2 electrons, so it forms a +2 charge. And then some of these get a little dicey. Boron forms a +3, everything in this column, but it doesn't include there's some, it's only the things above the stair-step line, which I don't have here, and I don't want to misdraw it. So boron +3, carbon is ±4. Wait, that's not how you write any of those things. So in this column, you're close to 8. Either way, you can lose 4 or you can gain 4, right? Because you have 4 valence electrons. Now it becomes, as you get to nitrogen, it becomes easier for you to gain electrons to get to 8. Remember, the magic number is 8. So instead of, when you're at nitrogen, you've got 5 valence electrons. What's easier? You're going to lose 5 electrons to get down to 8, or you're going to gain 3. And of course, you're going to gain 3. So all of these form a -3 charge. All of these form a -2 charge, -1 charge. And then these don't have a charge. And the reason is because they already have 8. So the noble gases don't form lots of compounds because they already have 8 valence electrons, so they're very stable. So they don't need to go through the situation where, oh, I would love to have 1 more electron there, or I would love to get rid of this electron so I can have 8, because the noble gases already have those 8, and so they're very, very stable. So this is the background on how to start combining these ionic compounds, or combining these elements to make ionic compounds. And what you really need to know is that for these columns that I've written there, those are the charges. And I mentioned too, these transition metals here, and some of them underneath the stair-step line there, whoops, I got a little crazy. All of those they can have more than 1 charge. We don't know their charges always, and that's because the d orbitals are very complicated. But for right now, the most important thing you can know is that these are the charges for those columns on the periodic table. And we're going to use those charges to write some ionic compounds right now. So here we have some rules for naming and formula writing for different kinds of ionic compounds. And we're going to start with what we call case 2. There's a very large packet, which you also have access to, that classifies all these different naming and formula writing rules by cases. I think it's helpful because there's a lot of exceptions, a lot of weird rules, and as a reminder, we are just learning how to name and write formulas. So when you see, like, for example, like sodium chloride down here, and you're like, what is that? It doesn't matter. We're not there yet. We're just learning about the rules to name and write formulas. That's really important. That's the only thing that you should be able to be good at after you're done with all of these different cases. Okay, so we start with case 2. You make sure you copy these down in your notebook or onto Notability. You can use this sheet as well. Case 2 are ionic compounds, which are metals and non-metals. And just a reminder, on the periodic table, the metals are on the left-hand side and the non-metals are on the right-hand side. And so it's a very large section with a very small section, but it still produces lots of different compounds. We'll get into what ionic compounds look like, what their properties are, but we're not doing that yet. We're just learning how to name and write their formula. So naming is the easiest case, so we'll start there. Ionic compounds, we call them binary when they have 2 things. And we're going to start with the easiest case, which are binary ionic compounds. So the rules are basically these. You name the first element, and that's the first one in the series, so like that one right there. And then you give the second element an IDE ending, and you get to ignore the numbers. Okay, so if there's numbers in the formula, you don't need to worry about them. It's a very straightforward rule. So when you see something like NaCl, you name the first one as sodium, and then the second one is chlorine, but you give it an IDE ending, so you call it chloride. So that is called sodium chloride. That's table salt. Second one, you get to ignore the numbers too, so that's really important. You don't need to do anything numbers-wise for case 2. So you name the first element, which is that one, and then give the second one an IDE ending. Go ahead and pause it, think about what that would be, maybe try to write it. And so the first one is barium, And the second one is nitrogen. Nitrogen is one of the weird ones for naming. It's called nitride. So that element is called barium nitride. There's a handful of other practice ones on a different sheet, the big packet, which we'll get to in a little bit. Okay, so that's naming the easiest case. Name the first one, give the second one an IDE ending. Writing the formulas for ionic compounds is a little more complicated. To write the formulas, you're going to need your periodic table, and it's going to have the charges on it. So if you haven't drawn the charges of all the things, you're going to do that now. So as a reminder, +1, +2, skippy skip, +3, plus or -4, -3, -2, -1, and 0 for the charges. Now when I say that charges, I mean everything in that column or group has that charge. So everything, for example, in this column here has a -1 charge. Everything in this column has a +2 charge. This is when you take away or add their electrons. So let's get back to the rules for naming and formula writing. For formula writing for ionic compounds, you want to write the charges first, and then you do this thing crisscross. When you crisscross, you don't write charges and you don't write ones, and that won't make any sense until I show you a handful of these, and I think it will be very helpful for you. So first thing you want to do is write the charges. So when you see calcium chloride as your example, you want to go and find the charge for calcium and find the charge for not chloride but chlorine, remember, because we're reversing what we've done for naming. So calcium's right here. Okay, it's got a +2 charge. So back up here, we write calcium +2. And then again, chloride, we're really looking for chlorine, right? Because chloride means it's already been named, so we've got to reverse that and look for chlorine. So chlorine would be a nonmetal, right? Because calcium's a metal. So chlorine right here is a nonmetal, and it's going to have a -1 charge, as you can see. So let's go back up there and write -1. And when you crisscross, it's a very simple mathematic trick. You're just taking these numbers or superscript and you're moving them down to the corners like this. That's it. And you don't write the charges and you don't write the ones. So what you're going to write instead is calcium, and then there's going to be one of those, and chlorine, 2 of those. So this is the formula for calcium chloride. That's how crisscross works. Don't write the charges. Notice the charges went away, and you don't write ones either. So the one that went down this way, you don't write that one. It's really just a little trick. What you're saying is if you've got a calcium, which is +2, and you've got a chlorine, which is -1, the reason that they're even bonding in the first place is they have to be neutral. They have to be 0. That's why they're doing this. They're transferring electrons to get neutral, to get the full octet, to get the magic number of 8. Okay, so to do that, what you're saying is, okay, well, I've got one calcium, and it's got a +2, and I've got one chlorine, which is a -1. So I'm going to need another chlorine to make this work, right? Because it's got to be neutral. It's got to be 0. So now these two charges would equal -2, and that would cancel out the 2 of calcium. And so as a result, your formula then is CaCl2. But the crisscross method works like 93% of the time. So I would just use that for the most part. Okay, we can try a couple other examples as well. Next one's magnesium phosphide. So let's go down to the periodic table, and you should pause it right now and try to write the formula for magnesium phosphide. So magnesium phosphide, oops, wrong one. If we look in the periodic table, we're looking for magnesium first. Magnesium is going to be a metal. It's right there. It's also a +2. And then phosphide, it's one of the challenging ones. Phosphide IDE was really phosphorus right there. And you can see that's a -3 charge. So we're going to write those up here. After we found the charges, we write magnesium, which is +2, phosphorus, which is -3. And then you crisscross. So the 3 goes down there and the 2 goes there. You don't write the charges and you don't write the ones. In this case, there are no ones, so that's not a problem. So the formula then is Mg3P2, magnesium phosphide. Again, the whole thing is bonding to be neutral, right? So what you're saying is if you want to get these two things to be neutral, you got Mg2, P-3, what's a common multiple of 2 and 3? You'd probably say 6, right? So I'm going to need, to get to +6, I'm going to need 3 of these, and get to -6, I'm going to need 1 or 2 of those, right? And then this side is +6, this side is -6, and so it cancels out, and I've got 2 phosphorus and 3 magnesium, 2 phosphorus. Okay, but the crisscross trick works a lot easier, but that is what is going on when we do the crisscross stuff. Oops, there's my old stuff. Spoiler alert, don't look at the second one. Oh, now I can't even erase it. What a terrible time. All right, so these things happen, though, sometimes. What are you going to do? So next one's calcium oxide. Let's take a look. Try calcium oxide. Calcium is right here, still a +2. They're not always +2, obviously. I just picked 3 that were. And the oxide is really oxygen, which is a -2. Okay, so there's one more thing that you need to know when you're doing these, calcium +2, oxygen -2. If you were to crisscross those, you would get Ca2O2. But one thing that you should do for all compounds is reduce them if you can. And since 2 and 2, they're the same, you can really reduce it as this, calcium oxide. They just cancel each other out. And again, that makes sense, right? Because you're saying you've got a calcium, which is +2, you've got an oxygen, which is -2. You're just going to need one of each to cancel them out, so the formula ends up being calcium oxide. Okay, there's a handful of other ones I want you to practice on a different sheet, but I will tell you about that in a different video or in some sort of homework assignment. This has been super fun. Congratulations on writing and naming your first kinds of compounds. Okay, well, give me a call. Bye.